All right, it's 4 o'clock. Good afternoon, everyone. Hope you all are doing well. I'm Zara Mohagek, an associate professor in the NPRE department. It's my pleasure today to introduce our seminar speaker, Dr. Elizabeth Paté-Cornell, a professor in the School of Engineering at Stanford University and a member of the U.S. National Academy of Engineering. Dr. Paté-Cornell's specialty is engineering risk analysis with applications to complex systems, focusing on probabilistic and stochastic models and artificial intelligence. She's the author of numerous publications and the recipient of many prestigious awards, including those from Society for Risk Analysis and the IEEE. With that, I would like to welcome Dr. Paté-Cornell to our graduate seminar.
Thank you, Zara. And perhaps we can get my picture on the side. No, but my picture so that they see me speaking.
We can see you. Everyone can see you.
Yes, but it will be easy if I can see myself.
I don't think we can do anything our side, but your side probably.
Okay. Let me see. No, it doesn't work. Okay. Well, I'm sorry.
We can see you on our screen. You have your face is visible to us.
Yes, we can see you.
It's not visible to me, but that's so that it's hard to. Okay, let's go back to the first page. Okay, and first page. Today I'm sorry that I cannot be with you, and I would love to see you in front of me. I'm going to tell you about the work that we have done in cyber risk, but particularly risk management of cyber attacks, that is trying to see them coming, the attacks, and do something before they do a lot of damage. And what is the role of artificial intelligence in all that? Next. Yes? Okay. Let me tell you what is our way of looking at risk analysis. First, we identify failure scenarios. Then we look at the uncertainties in each of these, in each of the components of the scenarios. And to do that, we use either statistics or Bayesian probability, but it has to be independent of preferences. So you're not going to twist the results to make it fit your preferences. Then we look at the outcomes. Then we do a dynamic analysis that includes, for example, the game against an adversary that's trying to attack us, and the updating of information as we learn more about these adversaries. The important thing is also to decide what is our time horizon. Next. Okay, let me tell you what my story will be today. So cyber risk analysis, we started our design and by the simple use of statistics when they exist, and they existed because we were given a big database that I will show you. And then we do systems analysis and probability if we don't have these statistics, because it's rare. And then I'm going to show you two vignettes of analytical methods, including artificial intelligence. The first one is what is the optimal level of connectivity in a system between the elements of the system and the cloud. And I'll give you a smart grid example. Second one, which is very popular these days, is this question of warnings and management of cyber attacks. So we are trying to identify and to stop the potential attackers. Next. So why do we do cyber risk analysis? Well, to avoid, as an alternative to guesstimates, 1 in 10, and or whatever comes from someone's hat, and blind or myopic spending. So what we are trying to do is to best allocate limited resources. And we are going to see what we mean for different types of attack. For example, on insurance, we were invited by Swiss Reinsurance as soon as we did this study. Next. Okay, so what were the top network attacks in 2022? Essentially phishing, and you know what it is because I'm sure you got it in your email, and ransomware. That is people who are capturing the software, let's say, of a hospital, and tell them that they will have their software back, their data back, if they pay large sums of money generally. And then you see the other possibilities. Next. Well, what are we trying to do? For a specific organization, that's important because this is a specific model that I'm going to show you. It's not a general policy analysis. It's what do you do if you're in a company and you have problems of cyber or potential problems of cyber risk. So we assess the risk, we decide whether it's acceptable or not, we identify the risk management options, and you're going to see what we're talking about. We assess the risks and the benefits of these options, and we set priorities given the budget constraints. And when I say budget, it's the resource constraint. So you're going to see that it involves teams of people. Next. Okay, how do we quantify the cyber risk? The mathematical approach is to construct risk curves, and those are the complementary cumulative probability distributions of annual losses. So that means the probabilities of exceeding different risk levels, different loss levels, I should have said. And there are three ways to capture uncertainties in these risk curves. One is a statistical analysis of data, and I'm going to show you that if they are available and relevant. I've seen a lot of statistics that were not really relevant because things had changed too much. The alternative is a probabilistic analysis based on scenarios, and generally we combine both because on the tail of the loss distribution, we need the probability. Next. Okay, we have a general risk analysis model, probabilistic, of course, and here's what we need to know. What's the nature of the target organization? For example, a hospital. What information needs to be protected? Well, the files of your people, of your employees, of your patients. What is the structure of the system, both physical and cyber? What's the structure of your computer system? What are the potential, the most likely adversaries? Who is interested in your stuff? People who want to steal your money often. And what are the consequences of a successful attack? So what analysis of information do we do? As I said, for known attacks, relevant statistical data sets. For events that have not happened yet, we do a structured Bayesian network to model the potential attack scenarios. Next. Okay, so I'm going to show you first the cyber risk research that we have done, starting with statistics. But then I'm going to show you two vignettes that are two serious studies of very specific problems. The first one is a network analysis of the optimal connectivity of your system, the elements of your system to the cloud. And we have an application here of a generic smart grid because we got all the data we wanted from the Sacramento Municipal Utility District. And it was done by Lieutenant Colonel Matt Smith, US Army, who is at the NSA now. That was his PhD. Then the PhD of Isaac Faber, also Lieutenant Colonel, who's at Carnegie Mellon, for the warnings and management of attacks. And so what I'm going to show you is an AI model of collaborative decisions between a robot and a human. And the decisions are to open or close the links in the network to let people enter, the good guys and the bad guys, try to stop the bad guys, recognizing them by their characteristics, but make sure that you let the good guys come in because they may be your clients. Next. Okay, so we start here from an empirical analysis of past incidents, and we extend that to new attacks. So we were working with one of the centers of NASA, and we had two distinct kinds of cyber attacks. The operational ones the routine attacks on your systems, for which statistics may have been gathered, and destructive attacks that have not happened yet, for example, a mission, yes, make a mission fail. So the distinction between the two may be fuzzy because you have close calls, but the data and the analysis are different, and I'm going to show you why. Next. Okay, so let's look at 3 examples of routine attacks and costs for that company. So email, website, stolen computers. They were particularly concerned about these stolen computers. And what are the costs of a successful attack? Well, the loss of intellectual and physical property, but also, of course, business interruption. Next. So our countermeasures, the most effective that they had were firewalls. Full disk encryption was really useful. Two-factor authentication, very useful. Data loss protection, for example, passwords, pins, etc. But you cannot make it too complicated. So the effectiveness of these measures depends, among other things, on the nature of the system attack, the type of attack, and there you are concerned also about insider attack. The ease of implementation. Do you want to require a 16-character password? People will not remember it. And the sophistication of the attackers. We're going to see that this is an important story. Next. So here is our statistical database of incidents. We will call it Space Corp because we're not supposed to talk about the organization itself. 60,000 incidents over 6 years for various routine attacks and the different costs. So you see, you have the date on the horizontal axis. You have the total cost in terms of hours of investigation on the vertical axis. And each of those circles represent an incident, and the more costly, the bigger the dot. So it gives you an idea of the kind of data that we got. Next. And the effectiveness of the countermeasures at Space Corp was relatively easy to assess given our method. And we looked at lost or stolen devices. And as you see, the change in rate was mostly due to reporting guidelines. And the rate of lost devices was remarkably consistent over time. And in this case, large incidents did not occur after full disk encryption was implemented. So that was one of the most important conclusions of our study, full disk encryption, and that will do good things. Next. Then let's look carefully at what the risk curves looks like. What I did is for each of the sources of attacks, the type of attack, I looked at what is the probability per year, there it is, of exceeding these annual costs. So this is what is called the complementary cumulative distribution function. So for example, here, I have a risk curve that represents the data spillage. You don't want to send data, but you do it anyway, and it spills over the internet. Okay, so a point here represents the probability, there it is, of exceeding per year this annual cost, there it is. So again, the probability that different costs are exceeded in a given year. So here you see emails. Here you see, let's see, website. And here you see the total cost, the total risk. These risk curves are the classic curves that we compute for anything. So we have generally statistics in the lower part of the losses. But the question is, of course, what's happening? What is the upper limit? The things that could happen, but we have not seen yet. And that's where we need to design scenarios based on expert opinions and see what we get. Next. So, yes, see, the loss for website compromises are usually small.
control away really fast.
I'm sorry, can you mute yourself, Jim?
It's like X, Y.
We have a problem. You may want to ask the people to turn off their
Okay, there's,
mute. Okay.
That's the best part. So you look at your camera and then if like someone wants to tell you this cool thing, this cool thing, this cool thing, and you have some other cyber.
could you please mute your microphone?
Tell them to mute. Please mute. Okay. Next. I'll take questions after that, so you don't have to.
Sorry about that. But you can go forward.
Next. Next. Okay, so I was saying sometimes they're huge. Now, how do we combine statistical models with scenarios? That is perhaps the most important thing. You may want to mute this. Okay, so first, in the first part of the curve, we have the data-driven model of past incidents. So those are the statistics. Then we construct the model of new possible attacks using scenarios. And there's an overlap here because some of the elements of these scenarios have been observed in past incidents. And so it's this curve that gives us a complete view of where the risk actually is. Next. Okay, let me give you another example. It was phishing. You train people to prevent them from responding to phishing. So we had a base rate of 20% people falling for the phishing. And we had two levels of training, one that reduced that to 15% and one that reduced it to 10%. And we looked at the corresponding risk curves. And as you can see, the base, of course, is above all the rest because so many people respond. The best is the user training that gives us only 10% response. And this is how we can compare the risk by comparing the three risk curves. Next. Now I'm going to show you, now that we've talked about statistics, that's the easy part, I'm going to show you two models. The first one is a network defense and looking for an optimal level of connectivity applied to this electric grid cybersecurity that I was talking about. The motivation was the first attack of that kind in Ukraine in 2015, when they faced the world's first blackout caused by hackers. And it was pretty nasty. It was December 2015. They coordinate a cyber attack against 3 distribution companies. They caused a lot of people to lose power for several hours. And it was the first known instance of cyber attack that caused power outage. Unfortunately, they're going to have a lot more now. Distribution companies were likely targeted because they were the most connected. And so it was easy to go from one to the other and to, we're going to see, they controlled the systems. Next. Okay, the challenge was that we had limited data on known incidents. We had multiple levels of scenario uncertainty because of the complexity of the engineered systems, but also the human behaviors. We had a trade-off between security and performance. I'm going to show you that trade-off. And tightly coupled critical infrastructure networks are prone to cascading failures, as you know. So the network analysis were designed to identify vulnerabilities, and vulnerabilities are these entry points in the system where the bad guys can enter it. So the question here was an optimal allocation of cyber defense teams. And those are the watchers, those that watch the vulnerabilities that we know about, versus the hunters, those that look for the new ones. And I'm going to show you how they do that. Next. So smart grid. Smartness adds communications and improve efficiency and reliability because it allows the grid systems and the operators to react intelligently to changing conditions, for example, the demand. But added connectivity, of course, increases the vulnerability because it opens new digital threats, such as denial of service attacks, etc. So that's the trade-off between smartness and added vulnerability. Next. Okay, so what was the network model? Well, a system operator that controls the physical power grid. The operator may choose to connect any subset of nodes. So we're going to see what the choice is on a figure. Each connected node enables a smart grid technology, but also becomes a potential vulnerability. So where do we want to concentrate the team's attention? Next. That is a good figure of the system, the overall system. On the ground here, you have the grid. And in the grid, we have a component of the grid. And you can see the smart ones are already connected to the cloud. And then you have the standard ones that are not yet connected to the ground. And the question is, do we want to connect this one to the cloud with the benefits that it has, but also the new vulnerability that it's going to bring? You see, for example, here, we have had already a cyber attack, so it's a known vulnerability. Same thing here. And the question is, are we going to introduce a new vulnerability by putting a link here? Okay. What are the benefits of smartness? Well, it can automate the processes that previously required human intervention. So before inspecting oil in a transformer, for example, now it's automated. We can detect routing outages more quickly, quicker detection of the outages due to vegetation. That's important, as you know, in fires. Easier integration of renewables, and because we can shape the system more easily, and improved market efficiency due to the demand response and enhanced network visibility. So here you have a control room and quicker adjustment of prices. But next, but the flip side is the cyber risks. And I'm giving you 3 examples here. Aurora in 2007 was the simulation of a cyber attack on the generator information, and it was publicly released by error. And that was unfortunate. The phantom mouse phenomenon, a software designed to take control of the mouse in a control center that's not yours. So you enter someone else's system and you take control of the mouse. And then the countdown to 0 day, WannaCry in 2017, ransomware of hospitals as target for the first time. Now, 5 years later, we have the same thing happening, unfortunately. Next. So what's the dynamics of cybersecurity investments? The question here is, what is the use we make of the cyber defense teams? The choice is exploitation of known vulnerabilities by the watchers versus exploration, find the new ones by the hunters. And it's a classic, what's called the multi-armed bandit problem in operations research. And I'm going to show you how it works. So this is what the defense system that my student photographed when they were at work. Next. Okay, so here is the model. Here's the classic operations research model that some of you may have seen. It's called the multi-armed bandit. So you're facing machines in a casino, and this one we know what's the probability of different outcomes. This one we do not know. It doesn't mean that it's not just as good, but we do not know, and this one we do not know either. In the same way, we have constructed a multi-node bandit model, and here are the elements, and entry nodes vulnerabilities here due to connections. This one we do not know. It's exactly like the first machine. This one we do not know, but it could be entered. This one we have seen already some vulnerabilities. It has been attacked in the past. So we have the same problem of choosing between not knowing the fundamentals or knowing the fundamentals and having uncertainties anyway, except that we know what they are. Next. Okay, so how do we search for optimal connectivity? First, systems analysis. We look at the classes of cyber failure scenarios. Second, the economic analysis. We look at the financial benefits and risk of increased connectivity. The third is the stochastic model. We use multi-node bandit security models to assess the trade-offs. And the fourth is the decision analysis to find the optimal smartness, given that we still have, of course, some uncertainties when the system managers make a decision. Next. Now, we were very lucky. Excuse me, just first. Very lucky because we had lots of data, real data, and their sources. The benefits were given to us by the utility company. The price and the customer demand data were obtained from the Energy Information Administration from the 2015 census data. The risks, including cascading effect of failures, were given to us by the North American Electricity Sector Cybersecurity Organization to quantify the consequences of failure scenarios. And all the illustrative data were given to us by the Sacramento Municipal Utility District. So this is a rare case in which to do a cyber risk analysis, you have all the data you want because people are happy to give them to you to help them protect their system. Next. So here is what we did. We computed the effect of the risk costs on the benefits as a function of the smartness. And the smartness, remember, is what proportion of the nodes are connected to the cloud. And for each of those, we looked at the benefits. And when we put the risks and the benefits, or the cost and the benefits together, we can find an optimum here in the net result. And that is the optimum level of smartness that we want to have. For example, ask yourself if you want to put your refrigerator on the internet to have it tell you that you need some milk. Next. So this is over. So we were lucky. We can go back one. We were lucky. In that model, we had the data, we had the conclusion, and we could give it to the customer, quote unquote. And now for something entirely different. And this one is very much, is very important and recognized as very important. It's warnings and management of cyber attacks. And again, by Colonel Faber, who's at Carnegie Mellon at the head of one of the AI groups of the Army. And the objective is to generate early signals of attack threats, that is, who are the bad guys, using AI in hybrid team decision makers. So the decisions to let them come in and move through our system or not are made both by a super expert, including a robot who reacts when they have all the information they need, and a human operator that the robot calls for when the robot is very sad. So the robot learns from the operator and makes decision to leave the circuit open or closed based on control software at each observed gate. And a gate is one step in the attack process. So the bad guys are moving through your system, and each step that they go through is a gate. So it goes on a human. No. Yes, yeah. It goes on a human if there is too much uncertainty or if the consequences are too big. So we need, and it learns with more information, and that's the machine learning part of AI. So the result is the ability to find an optimal security policy to let an input come in or not, given a signal. That's what we call a gate policy. Next. So our research method, first to develop machine learning techniques to move ahead and at the early stage of attack dynamics. We built and deployed a global honeypot sensor array. It's 18, we put up 18 honeypots to collect real world data about the attackers, see who is interested in us and what are their characteristics. Then we studied the communication system, and then we used industry standards attack graph, and that's called a kill chain. I'm going to show it to you. And it's what the bad guys do in sequence. Reconnaissance, weaponization, delivery of the malware that they have just designed, exploitation of that malware, installation, command and control, and then we're going to see actions on the objectives. Next. Okay, so the signals of threats are generated by artificial intelligence. The collaborative decisions between the robot and the human are made to maintain our systems links based on signals, uncertainties, and economics of outcomes. And we consider the effects of the outcomes of leaving a door open to a legitimate customer or an attacker, or closing it. And of course, there's, as I said, costs if you keep out a legitimate customer. And the decisions are based on a utility function that represent a predetermined risk attitude in the control system. And we're going to see the problem of having a predetermined risk attitude. So this is the cyber kill chain as represented by Lockheed Martin, the one that I just described earlier, reconnaissance, weaponization, etc. And signal identification and detection at every step of the cyber kill chain is what we're trying to get. So next, attacks are not single occurrences. We can see the bad guys coming back. Next. They range from a few simple steps to repeated elaborate events. And our objective is to learn the adversary's behavior patterns and to detect the stages of attacks in progress. Let me show you a timeline of an attack. It's just an example. So suppose it's a ransomware on a hospital, and I'm looking at the attacker's progression here. And we observe signals as gates. Well, it takes a few weeks for them to probe for vulnerabilities of the system that is finding entry points. Then it takes about 1 week to prepare the malware for a specific system. And then comes the implementation, takes only 1 week also. And then doing it, which is minutes. I mean, the attack itself is minutes. Deliver, exploit, control the host, execute the attack, maintain the control, and get the information out. Get the information out if that's what you're trying to do. Next. Okay. So what are the basic concepts? We look for actors, the bad guys, not initially the attacks. There are two broad categories of actors, the legitimate and the threats. The behaviors are the data about what we observe the actors doing, request entry, attack or not, what time of the day, how often do they do that, etc. So that's how we characterize. We characterize the bad guys and we recognize them. We develop a gate policy to optimize the system value based on the expected utility of decision outcomes. And our goal, again, is to block the threats and to allow the legitimate activity. Next. Now, this is a representation of what really happens. This is the system here. And this is the entry. So I put in blue the legitimate actors and in red the bad guys. And we have a hybrid team, decision team, that decides to close the gate, there it is, or to open the gate so that they can pass. Okay, so let's look at what's happening to this legitimate actor. Well, this legitimate actor, unfortunately, is blocked at the end at this gate. But this legitimate actor here goes straight to the output. The bad guys here are stopped early, but here the bad guys are going to the to have an impact, and because it reaches the output. So you see how the hybrid team has to make decisions to close or the gates or leave them open, given what they observe and the information that they have about the attackers. Next. So we set up 18 honeypots, and as you can see all over the world, here it is. The service providers were Azure, Amazon, and DigitalOcean. But what's interesting is the observation that we got 600,000, and with a unique IP address, roughly 29,000. The number on a blacklist was about 11,000, and a number with multiple entries, people who come back to visit you again, about 12,000. So this is what gives us some signals, some signals about a given actor. Next. Here is the honeypot. Okay, observing the real world behavior, information from our honeypot plus the critical stack is given to us so that we can look at the good guys and the bad guys. The honeypot has given us information from all over the world. The critical stack that we're going to talk about, for example, commercial companies that identify threats and put them on blacklist. And at that point, the geolocation of observed blacklist events came mostly from China. Russia does not appear here and showed in dark red, and the US, bizarrely, France. Okay, next. So raw data are obtained from the honeypots. The frequencies of attack behaviors are used to identify the threats. So we do a frequency analysis of the events collected by the honeypots. And then we update the probability of threat for each potential attacker with each event. We do a Bayesian updating of that probability. Next. Okay, so this is the whole system. Here you have the security stack, firewalls, intrusion detection systems, proxy that allow masking other devices behind the entrance, and protected network. Okay, so here we have the super agent you need to next to appear to have the robot show up. Next. Yes, so you have a super agent, you have the robot and a human agent. So there's a central database that gets information from the security stack and from external information. For example, other companies of the same kind have been attacked. And it's that information that goes to the super agent to make a decision, to close or open the gates. Next. So the elements of the system, the security stack, the external information, so intelligence report, industry information, etc., and the central database with a big data set that learns over time using internal and external information. Okay, so our decision model. We assume that threats and legitimate requests arrive at the same time, at the same gate, following a binomial distribution over time. The super agent must decide if the gate should be open or closed based on expected utility of outcomes, and this is the decision analysis part of it, and risk preference. So the input in the system for the robot and more informed decision from the operator when the robot does not have what it thinks it needs just by looking at the database. So opening or closing the gate is a decision on the part of the super agent, and it's controllable, but it's imperfect. That's the part of it that's important. Next. So decision at each point, you have actors that appear at that point, and the decision makers must decide to open or to close. And the utility of outcome to the organization is what determines the expected utility of each of the two options. Next. So, focusing on a central database, the robot observes an incoming signals. It gets the information from the database. It decides to open or close the gate in the optimal way. Then the result is observed, has it been an attack or not, and the database is updated based on that observation. And we also do Bayesian updating of the state of knowledge based on that new information. Next. So active learning now, it's the human AI trade-off. The robot makes decisions by default. So the expert makes the decision when there is little or low quality data or too much uncertainty. And the robot knows when to ask. And we assume that there is enough time for the operator to decide. Now, some of the gates require expert intervention for much longer until the robot becomes confident that it has enough data. And the assumption is that the system does not change and that there is learning. Next. Next. Okay, this is a very important figure. This is time. And these are the gates. And I have 15 gates. And at the beginning, it's the expert, the human being who makes decisions in red. But when the robot decides that it knows enough, then it takes over and makes the decisions here. But we have left open the possibility that the robot all of a sudden decides that it had started making decisions, but it's over its head, and it doesn't know how to respond to something that's happening to this gate. So it calls back to the human operator. So it's that dynamic of AI learning and decision-making that's essential here, because the operator can come back and take over when it's needed. Next. So AI in the decision mode, the question is preferences. You see, in the first stage, information does not generally involve a utility function or preferences, except perhaps on choosing the information that gathers. Now, the second stage, which is a decision, does involve a preference, and the utility is part of the software as long as the robot makes automatic decisions. Now, when the operator is handed out the more complex decisions, it is his or her risk attitude that prevails. So what are the takeaways of the warnings and decisions? One can use behaviors as signals of threat to make decisions, to open or close a gate early in the kill chain, because the system learns from its operations. The decision is both from a robot that follows the information and the decision rules encoded in a database, and a human who makes decisions when the robot doesn't have enough information, and the human can use a different risk attitude, recognizing that the problem is more complex than it's thought. Next. Okay, my general conclusions about cyber warnings. The perception of cyber risk is often apocalyptic. It may be so. But the real question is, no, yes, it is scary, but what do we do next? And risk decision analysis may bring some reality and rationality into these perceptions because they treat explicitly the scenarios and the uncertainties. Now, one of the difficulties that I've encountered often is to communicate the results. Where does that information come from? There is also very little actual quantitative analysis of cyber risk. And in that respect, our work is, well, I wouldn't say unique because there are other people who do that, but it's less frequent than just qualitative talking about it. So we need to understand the system structure. That's the first thing. And I've seen many organizations that did not know how it worked. To access existing data sets of past attacks and to create new ones, because it's key to the relevance of the results and the effectiveness of the countermeasures that we're going to adopt based on that system. And that's the end of my story. and I would be delighted to answer your questions. And now, Sarah, we can remove my, turn off my stuff and put my my face, if you can, in front of.
Awesome. Thank you very much for your interesting talk. I appreciate that. With that, we can open the floor for questions. If please raise your hand if you would like to ask a question.
I'd be delighted to have questions.
There's a comment today. I guess there's a comment in the chat. I don't know if you want to read it out loud or.
Yes.
It's from Hamad Khalid, and it says cyber attacks are likely to influence human performance inside the control room. Normally, we use classical or simulation-based human reliability analysis methods to model human performance, but in most of these methods, we do have information about scenarios. For cyber attacks, we lack information about failure scenarios. So how can we model human performance in case of cyber attacks? Do we need to update those HRA methods or develop new techniques?
You know, I am not entirely sure that I understood your question, but if I get it right, you're asking, where do the information come from, right?
Ahmad, would you like to explain your question yourself?
Or someone,
So
the sound.
thank you. Can you hear me?
Yes.
I can hear you.
So thanks for your presentation. Actually, I was curious about, we talked about lack of information about failure scenarios, because in case of a cyber attack, we do not have all the information about scenarios. So with that uncertainty in mind, how can we know, like, if we want to evaluate human performance in case of such kind of cyber attacks that could influence the human actions to mitigate that cyber attack? So how can we model that human performance or mitigating actions?
Excellent question. We have two sources of information: statistics and what we have observed in the past. We have observed some behaviors, we have observed some technical failures, and then we sometimes need expert opinions. In fact, we need often expert opinions in addition to that. So it's a mix, as very often in risk analysis, a mix of statistics, information, models, what is connected, and expert opinions for the elements of the scenarios for which we do not have that information. This is particularly true for the events that will have a very large consequence. The very rare events, some have never happened yet, for which we need some information based on people's experience and what it would take for these events to occur. Do I answer your question, Hamid?
Thank you. Thank you.
Any other questions?
Can you repeat the question of the first person who was talking to me?
That was the first person, actually.
Oh, excellent. Now I could hear you.
Yes. The next question is from Mohammed. Go ahead and ask question.
Yeah. Hi, can you hear me?
Yes.
I can hear you, Mohammed.
Okay, thank you for the interesting presentation. And my question is about, you talked about the digital attacks, cyber attacks, but what about social engineering attacks?
Yeah.
For example, the human might be the weakest person in the loop.
Yeah.
So some attacks on the confidential information may come from like stealing information from the human himself.
Yeah. What you're saying is insider attacks, right? It's a general problem of insider attacks. So who might have any interest in intervening and attacking the system, and what can we do about it? Then, I mean, these people generally are identified by organizations because they need money, because they are connected to wrong people. So it becomes then an analysis of the group of people who have access to the system. And that's a very classic problem, as you know, in cybersecurity. So getting to know in your organization who might need the money and what they can do. And then look sometimes what they have done. You observe what has been done by different actors, and you decide whether they are good guys or bad guys. The insiders, that is. Did I understand your question? Did I answer your question, Mohammed?
Yeah, actually, one part of the question about the insiders, but sometimes attackers may not be insiders, but they can exploit the humans who work in the company in some ways to their benefit without being known about it.
And that's the same problem. So either you identify the external attacker who is paying the people inside, or you identify the people inside who have strange behavior, strange spending patterns, and you connect that to an organization. There is no miracle here. It's your instinct, your good observations, keeping your eyes open.
Maybe a relevant question.
Thank you.
Sorry, Mom. Relevant question is how much in the cybersecurity field focused on modeling underlying phenomena for the initiating event or attack? For example, in the safety risk assessment, let's say for nuclear power, we talk about LOCA, and we start with crack and progression of crack and rupture, and then scenario inside the system and consequence. But why the crack happened is typically seismic, flood, etc. And in order to avoid that, typically they say, all right, place a plan in a specific location that has less exposure to seismic. But in terms of security, that initiation and underlying, it's related to social, political, international relationship, etc. And that's a very interesting modeling domain. And I don't know how much that underlying modeling is coupled with the rest of the story.
Okay, well, it's not very different from loss of current accident that you're referring to in nukes. And in fact, the problem of cybersecurity is not only a human problem, it has to do with the structure of your system and how connected it is to other systems. So the equivalent of a LOCA, I would say, would be the vulnerabilities inside the system. So first, you have to know the structure of your system and what are the entry points and what are the entry points linked to and who can access these entry points. And that's why very often in large organizations, not everybody can access all the entry points of the system. And one of the mistakes that has been made in more than one company is to give to people too much access to too many entry points in the system. So it's not a different problem in that sense, you see.
In terms of progression is yes, the same, but in terms of underlying intention of the attackers. So how do you model why attackers attacked? It's more related to social, behavioral, psychological, that sort of.
Well, you're totally right. Social and political. We look at the behaviors of Chinese attackers, okay? And they generally come from the Chinese army. And those are people who work at fixed times, come back all the time, etc. So you observe the behaviors of the outsiders. Because you also have the kids who have decided that they were going to try and they are successful.
I see.
So and those you will look because they come back several times. So if you see someone coming back, you where that comes from, okay? You see, well, what else? Yeah, so the frequency of visits, I would say, the timing of these visits. You have to look very carefully at who is interested in your system.
Interesting. Any other questions from the conference room, from those on Zoom? I see another hand. Please go ahead.
Yeah, hi there. So you were talking about the interactions, or at least the dynamic interactions between a human controller and the AI that you were using to learn about specific thresholds in terms of like identifying where an attacker, when an attacker would actually implement an attack. I guess you showed this one graph that was going between different gates and then a time value on the x-axis. I guess, is there a specific threshold in which the AI identifies when it cannot determine the problem, and that's when it hands it over to the human operator to make an expert decision? And I guess, like, what is that threshold based on? Because you could kind of, I guess, move that threshold around depending on the sensitivity of the system, I guess. But I guess, like, what's the basis for that threshold to where the AI wants the human's help?
You're totally right. Okay, there are two criteria in that threshold. What are the uncertainties, and what are the consequences of being wrong? And so the threshold is the result of a decision, an external decision that has been made at the time when the system is designed.
Okay.
And that threshold is entered in the system based on the fact that the organization has a risk attitude and has a value function, a utility for the outcomes that might show up. So this is part of the system design a priori.
Okay.
And
So,
in fact, the choice of that threshold is very important. You're totally right. Think of a military situation. For instance.
Interesting. Okay, so then you're even saying then, depending on the applications of the program, since the threshold is applied a priori, then it can vary then from application to application of where that threshold lies, depending on the consequences and uncertainties associated with the outcome.
Precisely.
Okay.
And the risk attitude of the corporation. Because look at the operator is going to take time to make a decision. The robot makes decisions immediately. The operator may say, well, where does that information come from? And they take time to understand the information. And that's sometimes a problem that we have between the evolution of the situation they are trying to master and the time that it's going to take the operator to understand the information and make the decision. So when the robot decides to pass the hand to the operator, it's at the cost of time.
Okay. All right. Interesting. No, thank you very much. That answered my question.
You're welcome.
Very good. Any other questions?
There's a question in the classroom.
Okay, go ahead.
Sure. Thank you, Dr. Paté-Cornell, for the presentation. So I have one comment and one question. So the first comment is related to the research topic one that you mentioned, like how smart is smart enough, to have, enough connectivity. I think, that reminds me of, the fact that now nuclear power plants, they are trying to integrate more automation technology or system into, the existing system. And I think the similar question would be how much should we integrate, those automation technologies to avoid, exposing our system to those digital threats. So that I think, that has the potential. PRA has the potential to help inform such decisions, similar to the case that you saw. That you presented in we can inform decision maker how much connectivity we should introduce into the smart grid. So that was my comment that I see, the similarity. But the second, the question that I have is related to the second research topic that you mentioned. I like the idea that we combine the benefits of AI and human experts, where we utilize the benefits of AI where we have data, so like abundant data, for example, and then when we don't have data, we use expert opinions. But my question is, what do you think about the applicability of this approach when we have to deal with those domains with limited data. For example, I'm talking about the development and deployment of new advanced reactors in the nuclear industry right now. We don't have a lot of data, but at the same time, we don't have much expert opinions. So I think that the final question would come to the fact that how we would quantify the uncertainty associated with the final prediction by AI regarding, like learning about the adversaries' behaviors and predict the attack. How uncertain is that result, given that we don't have much data, but at the same time, we don't have much expert opinions? What do you think about the applicability?
Yeah. So you're talking about the applicability to small modular nuclear reactors, but it's more general than that. And so what we do is to look at the uncertainties in the expert opinions. Okay, it's not the point that you want; it's a distribution, and you introduce these distributions in your computation. And so there are uncertainties about expert opinions. There are uncertainties about the performance of the technical parts of the system. And you know about those based on tests, based on systems analysis, based on experience with the different parts of those. And this is particularly true for nuclear reactors in other plants. And so you, as I always say, you do what you can with what you have. And you put probability distributions on all the uncertain elements of your model.
Yeah, thank you. Yeah, totally agree. Yeah.
And I've done it for many things, including space systems, including, so we represent our uncertainties, we combine them, and we come up with a recommendation for decision making. Yeah,
so I think we share the same, mentality here. So our research at, the NPRE department in the Soteria group directed by Zara, we also, think about how to predict the uncertainty or quantify the uncertainty associated with the outcome of, simulation model or automation technologies. We need to take into account, consider, quantify all sources of uncertainties. So all of those that you mentioned just now. So I think, I'm totally agree with on the same page with you regarding that. Yeah, and thank you for sharing your opinions. Yeah,
you're welcome, and thank you for your questions.
Thank you.
So I think that we have covered a lot of ground. We're just on time.
Yes, thank you very much, Dr. Paté-Cornell, for sharing your research with our student. We greatly appreciate your time. With that, I would like to thank also the audience. I hope you guys have a very nice evening. Thank you, Doc. Thank you, Elizabeth.
Thank you. I'm going to stop the recording now.
Sure.
Bye.
Take care.
Bye. Thank you.
Bye, everyone.
Bye-bye.
Bye-bye.